Hello everybody and welcome to the Carlum Cymru revision sessions. The session this evening will focus on uncertainties and will be presented by Jane Owen from Penglai School in Aberystwyth. This session will last around 45 minutes where Jane will run through the relevant content. If you have any questions during the session, then please use the question and answer section within the live event and we will do our best to answer. The session will be recorded and the recording and any relevant resources will be uploaded to the e-sgol website under the Carlum Cymru tab. Over to you, Jane.
Thank you very much, James. And yes, tonight is all about uncertainties, and we'll look at them from a basic level and hopefully build them up. We'll be looking at absolute uncertainties, we'll be looking at percentage uncertainties, and we'll be looking at what you do when you've got more than one thing, say, in a given calculation that has an uncertainty. Okay, so in front of us, we've got a few little measuring devices. So for example, here, there's a mass of a cube and it's measured there 112.85 grams. So when we look at our uncertainty, to find the absolute uncertainty in one given reading, we look at what we call the resolution of the instrument. Now, clearly, this instrument can read to the nearest plus or minus 0.01 of a gram. So if we want to work out the uncertainty, we call this the absolute uncertainty. It's only one reading that we have got. We haven't got any repeats or anything like that. We're only given one reading, and we can read it to the smallest division here, the 5 and the second decimal place. So we take that and we call that the resolution. So plus or minus 0.01 gram is equal to the resolution. And here, that is the same thing as the absolute uncertainty. So in order to work out what the percentage uncertainty is, we take 0.01 and we divide it by the actual value, 112.85, and we times it by 100%. And here it will be, if I put it into my calculator, it's a very, very small, I would say almost negligible, 0.009%. Okay, now notice that I have quoted my uncertainty here to one significant figure. Usually all the uncertainties, whether they're absolute or whether they are the percentage uncertainty, we quote it to one significant figure. But there is an exception to this. If for any reason the number starts with 1, wherever that 1 is, it doesn't matter where in terms of decimal places. If the number starts with 1, we give it to two significant figures. Because, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, you can understand it's one significant figure. But when you go over into the teens, then 10, 11, 12, 13, 14, you know, we don't go from 10 to 20 to 30 to 40, i.e. that's your one significant figure. Just for those teens, 11 to 20, we go to two significant figures. And that holds also for going, say, 0.7, 0.8, 0.9, and then you jump to 1.0, and then you don't then jump to 2, 3, 4, you go 1.1, 1.2, 1.3, 1.4. So if the number starts with 1, you can write your uncertainty, whether it be percentage or absolute, to two significant figures. And we'll come across this as we do some examples. But the general rule is one significant figure, unless it starts with a 1, and then we quote it to two significant figures. Okay, now very common, we have a ruler and we can measure that to the nearest 1 millimeter. So we say that for ruler measurements, plus or minus 0.1 of a centimeter, and so that's my length. And so we say the absolute uncertainty is equal to plus or minus 0.1 because that is the smallest division. So one of these here is the smallest division that I can measure. Now, I know some of you will go, well, I can read it to half a division. But actually, if you give that argument that you can read to half a division, you've got to put your naught in place. Well, that's half a division there. You've got to read it off at the other end. That's another half a division. You add half a division at the start and half a division at the end, and then you've got yourself one whole division. So actually, just remember that the resolution is the smallest reading you can possibly take. So for example, my length of the line up here is 6.1. So my resolution is 0.1 centimetre. And that, if you've only got one reading, is also the absolute uncertainty. So just take the smallest division. Don't overcomplicate it by going any more than that and pretend that you can read to the nearest half a division. I know in maths they go towards that, but in physics you could just go to the nearest division. So on that note, that length there of that line, the absolute uncertainty is also 0.1, the same as the resolution. And so if I want to find out the percentage uncertainty, all I have to do is take the absolute uncertainty, the 0.1, divide it by 6.1, get it as a ratio, and then times by 100%. And that comes out to be 1.6% here. And because it starts with a 1, I'm going to have to give it to two significant figures. Okay, all right, so there's an exception to the rule. It's usually one significant figure, but it starts with a 1, so I quote it to two significant figures. Okay, so moving on, if I now have an area that I want to measure, then I can look at the uncertainties. Now we know that the uncertainty is plus or minus the resolution in this case, because I've only got one reading for each, no repeats. So plus or minus 0.1 for both of these. And some of you will say, well, why can't I just add the 0.1 and the 0.1? We can't do that because the fraction of 0.1 compared to your length 6.1 is completely different to the fraction of the 0.1 compared to 3.2. So this is why we have to turn everything into percentage uncertainty, and then we can add up those uncertainties, because the area here is given by 6.1 times by 3.2, okay, and that comes out as 19.52 centimetre squared. And you might say to yourself, well, you've done too many significant figures there, and I have, all right? So the general rule is 2 or 3 significant figures, all right? My raw is 2, my raw is 2, so actually I should quote my final to 2 significant figures, but you are allowed one more, so 3 significant figures is perfectly acceptable. So I'll put that there. Okay, and I'll just leave it, I'll just park it. Now let's have a look at what the percentage uncertainties are, because the area can be found by the one length times by, say, the width. All right, and when you're dealing with percentage uncertainties, to work out the percentage uncertainty in the area, we don't times the percentage uncertainties. We find the percentage uncertainty in the length and we add to it the percentage uncertainty in the width. Okay, because we're using the length once, we're using the width once, so we add them up. So let's work out, we've already worked out this one. So the percentage uncertainty in 6.1 is 1.6%. The percentage in uncertainty in 3.2 comes out to be 0.1 over 3.2 times by 100%. So that comes out as 3.1%. But you're telling me it should be just one significant figure. And you are right. So I'm just going to get rid of the 0.1 and just have one significant figure. All right, 2 significant figures for this one because it starts with a 1. And so what I do here to get my percentage uncertainty in my area, I add the 1.6% to the 3%, and I'm going to get 4.6%. But it doesn't start with a 1, so I can round that to one significant figure, so that's 5%. Okay, so I can quote this now, 19.5 centimetres squared plus or minus 5%. Remember, you cannot add absolute uncertainties. You can only add percentage uncertainties because the ratio of the absolute to the measurement that you get is different in the different lengths. So now what we've got to do is find out what 5% is of 19.5. And 5% is going to be a little bit, it's something like this, plus or minus. Okay, so you do 5 over 100, i.e. 0.05, times by 19.5. You sort of got to undo your area to get out what the 5% is. And that comes out as plus or minus 0.975. A little bit tricky. Now, that no way do you quote uncertainties to 3 significant figures. It's meant to be to one significant figure. So here I'm going to have to round this to plus or minus 1. Now, I'm either going to put 1.0, okay, which is acceptable because it starts with a 1. Okay, so that would be centimetre squared. Okay, so I could have, so there's 2 possibilities of quoting this and I'd still get my marks correctly, all right? So 19.5 plus or minus 1.0, those decimal places of my uncertainty, my absolute uncertainty in my area, ties in with the last decimal place of my area. Now, considering that the original lengths were given to 2 significant figures each, I can give my area to 2 significant figures. And it is conceivable here just to quote it to one significant figure, even though actually I probably want to go with this one, the first one, more because I know that the first number is a 1 and I can do it to 2 significant figures. But I don't think that they would take away your mark for either of those answers. But if you put 19.5 plus or minus 1, they would take away the mark because this last decimal place, i.e. this unit place, has got to tie in with the last decimal place on the area, i.e. unit place. So there's got unit there, and then 0.0 ties in with the 0.5 here. So either of those, I'm going to put that one in brackets. I like the top one better. I've chosen some really nice numbers, haven't I? Anyway, okay, so now that's looking at my area. So you can see what's going to happen if I have my volume, all right? If I've got my volume, we know that volume equals the length times the width times the height. We've already got some of these percentages, so it's not going to take too much of a jump to go to volume now. So 1.4 is slightly different. So 1.4, I'll put that out, 0.1 divided by 1.4 times by 100% equals 7%. Remember, I can only add percentage uncertainty, so I've got to go through this laborious process of working out the percentage uncertainty each time, and so will you. Okay, so 3.2, that is goes to, it's not equal to, it goes to 3.2 is 3%. We'll notice my significant figures. I've got 1 there, and I've got 2 there. So the volume, let's calculate that, 6.1 times by 3.2 times by 1.4. Now the volume here is 27.3 centimetre cubed. I'll keep it in 3 significant figures. All right, I can always come back down to 2 significant figures, but while I'm working things out, I'll just have one more, and then I can see which way to go at the end. All right, so plus or minus. Now, to get my uncertainties, I'm going to have to add, so my percentage uncertainty in the volume will be my percentage uncertainty in the length, plus percentage uncertainty in the width, plus the percentage uncertainty in the height. So that's going to be 1.6% plus 7% plus 3%. Okay, so all of that is going to be equal to, have I got anything wrong here? I just want to check. So 10, 11, so 11.6%. Now, I don't write it like that. It starts with a 1, even though it's in the 10 place, it's still fine. It still starts with a 1. So I say plus or minus 12%. I do 2 significant figures because the first number starts with a 1. So now I work out what 12% is of that volume. 12% of that volume is 3.3 centimetre cubed. Now, okay, so that, how did I get that? What I do is I do 12 divided by 100, i.e. 0.12, times by 27.3. That's how I get my 3.3 there. All right, so, but that's not quite the answer that we want to give, because that should be to one significant figure. So the volume equals 27 centimetre cubed, don't forget your units, plus or minus 3 centimetre cubed. And this time I would recommend doing it with just the one significant figure to tie in, so that the decimal places are consistent with the calculated value of the volume. Okay, all right, so actually that ties in quite nicely. Now, I think I've seen an exam question where not only does it ask for volume, but it asks, for example, the density. And the density is given by mass divided by volume. So the percentage uncertainty in the density is given by the percentage uncertainty in the mass plus the percentage uncertainty in the volume, because the mass is once in the equation, the volume is once in the equation. So we have to add the percentage uncertainties together. All right, it doesn't matter whether it's divide, you're still using it once in the equation, so we just add them up. So if we say, for example, that the mass is, say, 120 grams, and let's say that the percentage uncertainty in the mass is 5%, I'm just making this up, I'm not using the mass from the previous scale that we had, so that the percentage uncertainty in the density would be 12% plus 5% equals 17%. All right, okay, so therefore, if I wanted to work out my density now, I've got my mass divided by my volume, 120 divided by my 27. So 120 divided by 27 equals 4.4. Now I'm just going to use grams per centimetre cubed. I'm not going to try and be clever and convert it into kilograms per metre cubed. Let's just stick with what we've got, keep it simple. Plus or minus 17%. Now I don't round the 17% to 20 because it starts with a 1. All right, I leave it to 2 significant figures. Now work out what 17% is. So 17 divided by 100, i.e. 0.17, times by 4.4. I hope I've got this right. And sir, I hope you're going to correct me if I'm wrong. Times by 4.4 equals, so equals 0.75. Okay, so how are we going to write this? 4.4 grams per centimetre cubed plus or minus 0. Now this is 0.748. Okay, so I can't round this to 0.8. Okay, I'll have to round it down to 0.7 grams per centimetre cubed. Only one significant figure because it doesn't start with a 1. And that decimal place ties in with the 2 significant figure, the last decimal place of the calculated quantity. And actually, that ties in beautifully. Okay, I think that's probably one of the hardest things to see because it's your last mark. So you do all of this working and you get this far and you rush through and you've been careful, and then your final kind of like statement of what you are showing in terms of the uncertainty and tying in with the final value, that is very often where candidates kind of like just rush a little bit too much and don't look at it and see if it ties in. And this is, you know, kind of like I say to my guys, look, we're happy now. Look, it ties in. We're happy because, you know, it's the same number of decimal place. The uncertainty, the absolute uncertainty in the density and the final decimal place of the calculated quantity. Now, before we carry on, okay, that's good. We've done quite a lot already, and that's kind of like deep into the uncertainties. It does actually get a little bit simpler if you, for example, just had a cube. Now, if I had the cube up here, and this is like 6.1 and 6.1 and 6.1, so every kind of dimension is 6.1, then it does make your life a little bit easier because you know that the volume is given by, say, the length cubed. And because you're using that length 3 times in the equation, then whatever the uncertainty is of your 6.1, i.e. plus or minus 0.1, i.e. the 1.6%, you add the 1.6 or together 3 times. So i.e. you can just do the exponential 3 times by 1.6% to get your percentage uncertainty in your volume for a cube. All right, that's if all of the measurements are the same. All right, I'll just do it so that it looks consistent. Now, so 1.6, 1.6 times by 3 is 4.8, so 4.8%. So actually, when it's a cube, it's, in a sense, it's easier because you only have to work out the uncertainty once and then you can times it by 3. And this also holds, you know, like if you've got a sphere, it's pi r, 4/3 pi r cubed for the volume, then you can times the whatever the radius uncertainty is or the diameter, because the diameter and the radius uncertainty, percentage uncertainty, will be the same. And then you can work out times that by 3 because you're using it 3 times in the equation. So and we would write it to one significant figure. So the percentage uncertainty in the volume here would be plus or minus 5%. So should we just finish that off or should we move on? I think we just move on because you've got the idea. You've got the idea. Now, before we go on to kind of like other looking at other uncertainties and how you deal with them, have a look at these 2 measuring devices. Now, we've already done the ruler where the resolution is plus or minus 0.1 centimetre. Now, what I've got here at the top here is what we call a vernier scale. You might have seen these and you might have been given a digital one as opposed to a manual one. And a vernier scale can read to the, if it's manual, all right, can read to the plus or minus 0.01 of a centimetre, i.e. it's 10 times more precise, i.e. the resolution is 10 times greater. All right, but if you've got a digital one can read to the plus or minus 0.001 centimetre. All right, now if I just expand this, I'll just show you how to read it because it might not seem important to you, but you might have to come across it. Okay, so this reading here, now it can either go on the inside of pipes here, across here, where you put it in, or this will be on the outside of a pipe here, and you just kind of like tighten it ever so so that it just holds, so that actually you can pull the device out and you can still read the scale. Now this 0 here, this 0 mark here, is in between 3.1 and 3.2. So clearly this measurement is going to be 3.1 something. And then you track. I mean, okay, if you're using a digital one, a digital will just give you a straight read off. And the resolution will be whatever that last decimal place is that it can read to. It'll be plus or minus 0.001 of that. Okay, right. But I just want to show you how to read it because it is a useful skill to have. Now, this clearly doglegs with one of the lines above it. So what you have to do is you have to go along until you have a perfect match. Now we have a perfect match here. You have to go along on the bottom row and you can see there's a dog leg here, no, dog leg here, no, dog leg here, no, dog leg here, and keep going along. It looks like a dog leg, it's like a little bit crooked. All right, it's not dead straight. And keep going along the bottom bit here until it matches perfectly at the top. Now it's either that one or it's that one. I'm going to go with that first one actually, I think. Yeah, it's either one or two of those. I'm going to go with this one here. I tell you why, because usually you don't have these measurements, all right, on a manual vernier scale. So I go all the way along and I've gone to 8. So that is 3.18. And it ties in because that naught is closer to the 3.2 than it is to the 3.1. So I know it's towards the other end. So that reads off 3.18 centimetre. Okay, and I will just get rid of that. So what's the resolution here? That would be plus or minus 0.01 of a centimetre. And I am ignoring all of these little halfway in between because that's what you don't see on the school vernier calipers. Now, the other one is a micrometer screw gauge. So this is a micrometer screw gauge, and this has even got a greater resolution. So this one, okay, now if I expand it, each of these are a millimeter. The ones underneath, 0.5 millimeter. This turns here all the way around. Okay, this is a manual one. And this turns all the way around so that it turns once every 0.5 millimeter. So this line down the middle lines up and you've got a reading here of 0.14 that you add on to the 5 millimeters because it's in between 5 and 5.5. Okay, because I can't see the 0.5 line here. So it must be between 5 and 5.5. So therefore I go 5 and then add on to that 1.4 millimeters. Okay, so the manual resolution for a micrometer screw gauge is plus or minus 0.01 of a millimeter, i.e. plus or minus 0.001 of a centimeter, which I'm hoping is 10 times smaller than the, 10 times more precise, 10 times greater resolution than the manual vernier scale. Now, if you have a digital one, of course, we can read it to even greater precision, plus or minus 0.001 millimeter or plus or minus 0.0001 centimeter. Okay, so it's even, so it just depends what you get given, you know, at your school, but it's worth being able to read them manually. I hate to think that you've been preparing yourself looking at it digitally and just reading it off, and then they give you one of these that you've got to read off. Okay, right, now so we have done all of those uncertainties there so far, looking at only one reading. What happens if we have repeats? Well, we ought to take repeats, all right, especially if we got, for example, you've got a diameter of a bar, and let's just say, for sake of argument, that the radius here, I'll expand a little bit. Okay, let's go a little bit more further in, and let's say that the radius here, or actually let's go with the diameter. The diameter, because that's what you would read with a micrometer, screw gauge, or a vernier scale. Let's say that the diameter here is 6.1 centimeters, i.e. the percentage uncertainty. Now, if we go with let's just go with a ruler this time instead of a vernier, but perhaps we ought to vary it a little bit. No, let's just stick with the same because there's quite a lot that I still want to carry on with. So your percentage uncertainty in that diameter is equal to 1.6%. All right, and then to work out the area there is pi r squared, i.e. r equals diameter over 2, so equals pi d squared over 4, i.e. I'm using my diameter twice, so therefore your percentage uncertainty in your area is given by 1.6 times by 2 because I'm using it twice, i.e. 3.2%, i.e. 3% because it doesn't start with a 1. And if I have and add a length to that so that I want to work out my volume, then the percentage uncertainty in the volume, all right, given that the volume equals the area times by the length, all right, is given by the percentage uncertainty in the area plus the percentage uncertainty in the length. So let's have one of our previous ones for length. Let's just say that that is 3.2 centimeters again. So then my percentage uncertainty in my length is 3%. Okay, all right, I'm still using a ruler to do all of this. All right, I haven't used a vernier or micrometer, otherwise these uncertainties would be a lot smaller. So plus 3% for the area, 3% for the length. So that is equal to 6%, all right, in the volume. Okay, all right, so that kind of like gives you what you have to do. Okay, so we've done it for area, we've done it for volume. Given that, you know, the radius, because the diameter is divided by 2, whatever the percentage uncertainty is in your diameter will be the same as your percentage uncertainty in your radius. But the absolute uncertainties, even though they would be the same, the fraction as a whole would be different, and that's why you have to add up the percentage uncertainties. So we've done it for volume, we've done it for area, we've done it for density. Now let's have a look what happens when you have a repeated. Now I'm going to take a different color now, all right, because it's going to be far easier. Now we have got here some measurements. We've taken voltage and current for different lengths of wire, and I've just put 3 down here. So for the length, the resolution is plus or minus 0.1 of a centimeter. And very often you put this at the top of your table for any kind of like raw readings so that you can see that that is consistent with what we've written down in our table. All right, and because we haven't got any more readings for each one of them, there's no repeats in the length, so we can say that our resolution is the plus or minus 0.1, and that's the same as the uncertainty is plus or minus 0.1 centimeter. And again, with the voltage here, I can read it to the nearest 0.01. So my resolution of my equipment is 0.01 of a volt. So therefore, my resolution is plus or minus 0.01 volt, and my uncertainty would be plus or minus 0.01 volt. Now it gets a little bit more difficult when you look at the currents, because you can see here that the currents, I've taken 3 of them. First of all, you've got to look at all of those uncertainties, values, and say, oh, are there any anomalies? So these are pretty close together, happy. These are pretty close together, happy. These are pretty close together, this is way out. So I'm going to cross that off. So what I've done is I've identified an anomaly, and I'm going to take it out of my calculations for the uncertainty. Now, what I do for the uncertainty in repeated readings is take the maximum, take the minimum, find out what the range is, so 0.98, take away 0.92, and then halve it. And that is how you find the uncertainty in the current. So you take the maximum, 0.79, take away the minimum, 0.79, take away 0.74, and divide it by 2. And here it's going to be much easier, 0.63, take away 0.61, and divide it by 2. Right, now we've got to do a little bit of calculation. Okay, and let's have a look what we've got. So 0.98 take 0.92 equals, divided by 2 equals, and 0.03, nice and easy. I haven't had to go and slip into the second significant figures. 0.79 minus 0.74 divided by 2 equals, oh, okay, I've got 0.025 here. All right, so actually I'm going to round that, okay, to one significant figure, because it doesn't start with a 1, so 0.03. Okay, and then the last one is 0.02 divided by 2 equals 0.01. Okay, so I'm going to round what we are going to quote, all right, as our uncertainty in I. So that means, what is our percentage uncertainty? Well, you take your uncertainty, oh, we've got to find the mean first. So we're going to have to add them all up. So 0.98 plus 0.94 plus 0.92 equals, divided by 3 equals 0. Now I've got this 946 recurring like that, but I wouldn't write it like that. Be consistent with what the other currents are. So you're going to have to round those to 2 decimal places to be consistent with all the others. All right, now, so therefore, to work out what my uncertainty is in the current, I get my my percentage uncertainty in the current, I get my absolute uncertainty, I half the range, and I divide it by the mean, 0.95, and then times it by 100%. Okay, so let's do that now, 0.03 divided by 0.95 times by 100 equals, okay, 3.2%. So actually it's just 3. And that is what we quote to one significant figure. Okay, so if I have got now, and I've got to work out my resistance, I got my mean I, 0.95 here. To work out my percentage uncertainty in R, then I will take my, because R equals the voltage divided by the current, let's do that now. So 2.51 divided by 0.95 equals 2.6, and I can leave it to 2 significant figures. I can go to 1 more, but I'll go to 2. I'll leave it to 2 significant figures, and then your percentage uncertainty in your R would be whatever your percentage uncertainty in your voltage, and add to that your percentage uncertainty in your current. So for the first one, we've got 3%. So for here, that would be 3% plus. Now, what is your percentage uncertainty in your voltage? It will be plus 0.01 divided by 2.51 times by 100%. Let's do that, see if it's significant. 0.01. I don't think it is. 2.51 equals times by 100 equals, oh, it's 0.4% plus 0.4%. So actually we say that it's not very significant because it's not going to change, all right, because we only quote that to one significant figure, so 3%. So now what is 3%? So if you times 2.6 times by 3 over 100, all right, to get 3% of it, 2.6 times by 0.03 equals 0.08. So the percentage uncertainty would be 0.08. So we say 2.6 plus or minus plus or minus 0.08, and you can see my own undoing here. So I'm going to quote the resistance to 3 significant figures for consistency. So 2.51 divided by 0.95 equals 2.64, and that actually now that ties in because that now ties in with that decimal place. Okay, right, but you get the idea. What I'm trying to get to you here is if you have got just one significant figure, one reading, then you take the resolution and you just work it out as a fraction and you times it by 100%. And then if you've got to put subsequent calculations and you've got to use those uncertainties, then you just add them up however many times that you use those in the calculation. It gets a little bit more complicated if you've got repeat readings. The repeat readings, in that case, you are going to have to find half the range to get the absolute uncertainty, and then get that as a fraction of the mean and times it by 100 to get the percentage uncertainty. And then you carry on. Now, I've given a worked example here, so I'll leave that there. There's only one thing that I can really see wrong with it, and that is I've done too many significant figures here. So actually this is a candidate's response to the volume of this. They haven't got their units right, but we won't worry about that bit. And you can see what they've done. They have done their uncertainty and they've times it by 3. So we can't do that. What we've got to do is we've got to work it out as a fraction. So they've got 1 uncertainty, 2 uncertainties, 3 uncertainties, and then we add them all together. So, but can you see that this doesn't tie in with this? We've got to write this as 137 plus or minus 11. And really we ought to have centimetre cubed there and centimetre cubed here. So we can see there was a lot wrong with this one up here. Bless them, they tried, but now you know how to do it. There's a lot of work there, isn't there? There's a lot more work than you probably anticipate. Now, there's only one little thing that I've seen that pop up that I just want to address before I finish, all right? Now, if you've got to, for example, work out a square root of something, then the exponential of that is m to the half. Now, this is the only case where the uncertainties don't kind of like increase and add up. Whether you divide it, whether you square it, whether you cube it, all right, it's in the case of an exponential where it's a half, i.e. a square root. So let's say, for example, that it's 10% is the uncertainty in the mass. All right, therefore, what we do here is we have to times the 10% by a half because that is the exponential of a square root. And therefore, that the percentage uncertainty in square root m will be half of 10%, i.e. 5%. And that's the only time where it goes down. Now, I want you to remember it by timesing it by a half, not the idea of dividing it by 2, but timesing it by a half. I know it's the same thing, but kind of like, you know, then you never actually divide. Okay, and what I've got there is I kind of like estimating uncertainties. So now I'm hoping you can express your uncertainties by adding you know, a single uncertainty looking at the resolution of a single reading. You can, and that's usually whatever the resolution of the equipment is. Then if you've got a range and if you've got repeated readings, you use the spread of the readings and divide it by 2. And the reason why you divide it by 2 here is to give you that plus or minus. All right, so that because you've got the mean and how much do you add and how much do you take to give you that plus minus, that uncertainty. And then you've got to just get that as a ratio of the mean value to give you the percentage uncertainty. And I think I have now come to the end of my presentation. So well done. I didn't cover, yes, uncertainty in time. Uncertainty in time, you look at the reaction time. So for example, time plus or minus 0.2 seconds, you'd use that as the uncertainty, which is different to the resolution of a timer being 0.01 of a second. Okay, I think I've covered it all, and back over to you, James. Thank you.
Brilliant. Thank you, Jane. That was excellent. And I hope you all found today's session useful. Next week's sessions will focus on wave basics. And I believe, Jane, you're going to be doing something on gravitation.
Yes, fields, comparing fields for year 13, but this is year
comparing
12.
Fields, gravitational
You're
and
doing next
electric
week
fields.
on year 12.
Yeah, that's
Good.
right. So,
okay.
Thank you very much, everyone. And I hope to see you next week. And goodbye from us.